Hello friends, myself Jitendra Kumar. I am taking electrical machine design for the electrical engineering students of the 7th semester. Now in continuation of the previous lecture, we are just discussing in the another topic of the machine, which is called the thermal consideration. Thermal consideration, you already knowing that it will be associated with the temperature related parameter which is associated while we have to just look over the machine. Whenever it will be rotating, then automatically some parameter will be changes over there. Some losses are there, and that losses will be generate the heat over the system. So, the thermal consideration is an important parameter while we have to decide about the insulations of the machine, type of material we are opting over there, and so on. So first thing under this one is the conduction. This mode of dissipation of heat is important in the case of solid parts of machine like copper, iron, and the insulation of the machine. Conduction is the transfer of energy through matter from particle to particle. It is the transfer and distribution of heat energy from atom to atom within a substance. For example, a spoon in a cup of hot soup becomes warmer because the heat from the soup is conducted along the spoon. So the conduction is most effective in solids, but it can happen in fluids also. Consider 2 points in an electric circuit having potentials V1 and V2. The current flowing between them, so current will be there. So I equal to the difference of the voltage, potential difference of the V1 and the V2 dividing by the resistance offered by the material, where R is the electric resistance of the conducting medium between them. Similarly, if we are looking, we can write the equation for heat flow for conduction between two surfaces which are separated by a heat conducting medium as Q cone equal to theta 1 minus theta 2. It will be the difference between the temperatures, and R theta will be the thermal resistance which will offer a combination of this. So where we have to just compare about the electrical equation with the thermal equation. So where Q cone is the heat dissipated by the conduction, theta 1, theta 2, temperature of two bounding surfaces. R theta stands for the thermal resistance of the conducting medium under the thermal cone. Thermal resistance. The thermal resistance is defined as the thermal resistance which causes a drop of 1 degree Celsius per watt of heat flow. The thermal resistance, like electrical resistance, can be written as R theta equal to rho T upon S or T upon sigma into S, where rho stands for the thermal resistivity of the material, sigma equal to 1 upon rho, also called the thermal conductivity, T is the length of the medium in meter, and S stands for the area of surface separated by the medium. Q cone equal to the S into theta 1 minus theta 2 upon rho T. Heat dissipated per unit surface area by conduction is also indicated as a small q cone equal to theta 1 minus theta 2 upon rho T. The temperature difference across the conducting medium, it can be written as a theta equal to theta 1 minus theta 2 or q cone into r theta or q cone into rho T upon S. From the above question, it is clear that a material having high value of thermal resistivity will dissipate less amount of heat, or alternatively for the dissipation of same heat the temperature rise will be higher. So we have preferred a value having a high thermal resistivity will be associated with the high temperature rise. These are the basic property of the material. For example, if we are taken a air, a still air, there is a 20 ohm per ohm meter as the thermal resistivity. For the cotton cloth, it will be 14. For the micanite, it will be 8. For the compressed paper, it will be 8. For the paper, simple paper, it will be 7.5. For transformer oil, it will be 6.25. Press board, it will be 6. Varnish cloth, it will be 5. Mica tape, it will be 2.6 to 6.6. Asbestos, it will be 4. Empire cloth mica, it will be 3. Sheet steel, it will be along laminations or across lamination, it will be 0.02 or 0.05 to zero point 0.1. For a brass, it will be zero point 0.01. For aluminium, it will be 0.005. For the copper, it will be 0.0026. So the thermal resistivity of the material which we normally obtain for the electrical, like the aluminum or the copper, we are finding that it will be too low value will be offered by the sun. On the above table, we have rho equal to 20 for air and rho equal to 7.5 for the paper. Air has greater thermal resistivity than paper, and thus the presence of air packets in the insulation of the machine would have disastrous effect on heat dissipation, resulting in large temperature rises. The other parameter is the radiation. Radiation is the emission or transmission of energy in the form of waves or particles through space or through a material medium. Electromagnetic waves that directly transport energy through space. Sunlight is a form of radiation that is radiated through space to our planet without the aid of fluids or solids. The energy travels through nothingness. The sun transfers heat through space because there are no solids between the sun and our planet. Convection is not responsible for bringing heat to Earth. Since there are no fluids in space, convection is not responsible for transferring the heat. Thus, radiation brings heat to our planet. The heat dissipated by radiation from a sun depend upon its temperature and its other characteristics like their color, their roughness, and etc. For the case of a very small spherical radiating surface inside a large and or black spherical cell, the heat radiated per unit surface is given by Stephen Boltzmann law. The Q radiation equal to 5.7 times 10 to the power minus 8 e power T1 raised to the power 4 to minus T naught by 4 watt per meter square, where T1 and T naught is the absolute temperature of the emitting surface and the ambient medium respectively in degree Kelvin. Theta 1 and theta naught is the temperatures of the emitting surface and the ambient medium respectively. Also indicate the coefficient of the emissivity and equal to 1 for the perfect black bodies and is always less than unity for the other types of material. The above equation can be written as Q hat equal to 5.7 into 10 to the power minus 8 E T1 minus T naught T1 Q plus T1 square T naught plus T1 T naught Q square plus T naught Q. So now if we are assumed that the T1 minus T naught equal to 273 plus theta minus 273 plus theta 2, then there will be the value of the theta 1 equal theta 1 minus theta naught equal to theta, because from 273 will be subtracted from the 273 and the theta 1 will be the difference of the, and T1 minus T2 will be the difference of the theta 1 minus theta naught, or can be written as the theta. Represents the temperature rise of the body above the ambient temperature. The last term varies relatively little within conventional temperature limit Latte machine, and so on. We are just neglecting all these parameters. So we are getting a new equation which will indicate it as a Q rad equal to 5.7 into 10 to the power minus 8 E power KR into theta T1 minus T naught, or we can convert in the respect of the theta 1 and theta 2, where KR is the T1Q plus T1 square T naught plus T1 T naught square plus T naught TQ. The value of E for cast iron or steel surface, varnish or insulation, etc., is between zero point 0.9 to 0.97. Assuming a value of 0.83 for safety, we have Q rad equal to 5.7 into 10 power minus 8 into 0.83 kr theta 1 minus theta 2. So it comes out 4.8 into 10 power minus 8 kr theta 1 minus theta 2. So lambda rate equal to theta 1 minus theta 2. where lambda radiation equal to 4.8 into 10 minus 8 will be assumed as a constant for the so modified specific heat dissipation or emissivity measured in watt per meter square at a temperature rise of 1 degree Celsius. Its value depends upon the temperature theta 1 and theta naught, and hence it is not a constant value. It can vary as the temperature will be increases or the rotation of the machine will be going on, the temperature will be changes in a fraction of second. So the total heat dissipated by radiation is Q rad equal to small q rad into surface S. Lambda rad equal to theta into S in the form of a watt. In electrical rotating machines and transformers, radiation does not normally occur by itself, and in almost every case it is accompanied by the convection. Therefore, the following expression may be used: Q rad equal to 2.9 E times theta raised to power 1.17 watt per meter square. So for aluminum, the emissivity E equal to 0.1. For absorption factor, EA equal to 0.15. For copper, it will be 0.15. For steel, if the surface is rough, then it will be 0.24. If it will be a sheet, then it will be zero point 0.5. If it will be a metal paint aluminum, then it will be 0.55. For lead paint, if it's a white, then the value is zero point 0.9 or absorption factor is 0.25. If it's gray, then it will be 0.95 and absorption factor is 0.7. From the above table, the value of the coefficient of emissivity for dull metallic paint is zero point 0.9, while for polished metal it is 0.15. This means that the specific heat dissipation due to radiation for surfaces painted with dull metallic paints, usually gray in color, is large. Means all the electrical machines are painted with dull metallic paints in order to have a large heat dissipation due to radiation. So these are the specific parameters which is the most important while we are looking over the radiations and the conduction of the machine. Now thank you for attending the lecture. Thank you.